So hopefully you had an opportunity to work through this problem. If you haven't, please pause this and try to work through this problem on your own. If you have worked through and you weren't able to get to the solution, then probably a good time to try to look at it. All right, so we have the double integral e to the y squared over some given region, with the region being from 0 to 1 on the y and then from 0 to y on the x. So just like the previous example, start by letting the first integral go from 0 to the variable, or for whatever the bounds given by the variables. So integral 0 to 1, that's our y. Integral 0 to y. All right, so again, that one goes first. We have e to the y square. And notice that x is the first variable that we've tried to look at with respect to these two. So we're going to have dx dy as our order of integration. I also want you to notice that as it is, the integrand is impossible to evaluate over the real numbers just by doing it in terms of y. All right, and most of the time that's the case. All right, this is actually a really easy one to do at this point. So now we're going to evaluate. When we evaluate, now we get the integral from 0 to 1. We have x as the antiderivative of 1, or just dx, e to the y square, and x is going to range from 0 to y. And we still have our dy in there. We're going to use fundamental theorem of calculus. Fundamental theorem of calculus says top minus bottom. So now we have in the bounds. So integral 0 to 1. We're going to substitute y in for x. We're going to substitute 0 in for x. So that's going to be y minus 0 e to the y square dy. All right? Or if I were to rewrite that one last time for another integration, that would be integral from 0 to 1 y e to the y square dy. Now we're down to a single integral, so now it's a calculus 2 problem. Notice that this is not a fundamental antiderivative. It actually requires a u substitution. In this example, u is going to be equal to y square. The derivative of y squared, or du, is going to be 2y dy. And that's good news because we have a y dy, but we don't have a 2 in there. So what we're going to do is we're just going to divide both sides by 2 to be able to isolate y dy. And then we can substitute, and now we can get our integral solely in terms of u and make it a very easy integral to evaluate. We now get the integral from a to b. I want you to notice the bounds have changed because we're going into a different variable. We're not in terms of y anymore, we're in terms of u. Instead of y square, we're going to substitute u. Instead of y dy, we're going to substitute du over 2. And at this point, it becomes a very trivial integral. We're going to get 1/2 e to the u from a to b, since the antiderivative of e to the u is e to the u. We're going to back substitute for u. So this becomes 1/2 e. Recall that u was y square. Recall that the bounds of y were from 0 to 1. At this point, we're going to use the fundamental theorem of calculus. We have 1/2. We're going to substitute 1 in for y. So e to the 1 square. We're going to substitute 0 for y. So we have 1/2 e to the 1 square minus e to the 0 square. Another way to write this, 1/2 e to the first minus e to the 0. And then finally, another way to write it would be 1/2 quantity e minus 1. Still a third way to write it, e minus 1 over 2. That's probably the best looking answer, although all of the answers are fairly good looking. So hopefully this helps you to understand how we're going to simply evaluate but not set up In the next sections, what we're going to do is we're going to take this a step further, and we are going to set up the double integrals over general regions.